Right, I see the time is up, so let's actually get started. Hello, everyone. Welcome back to the AI Agent Frontier Seminar. Today, we are very excited to have Professor Daniel Fried. Daniel is an assistant professor in the Language Technologies Institute at CMU. His research is at the intersection of NLP, grounding, and interaction, with a specific focus on how we can build better language interfaces through agents and code generation. Before joining CMU, Daniel was a postdoc at Meta AI and UW, and he completed his PhD at UC Berkeley. Go Bears! His work has been recognized with Google PhD Fellowship and Okawa Research Award. Today, Daniel is going to discuss a fascinating topic, inducing and using abstractions of agent actions. As usual, we'll have about 45 minutes for the talk, followed by 15 minutes for Q&A. Please feel free to use your microphones for those questions or type in the chat. Be happy to read it for you. Again, Daniel, thank you so much for joining us. The floor is yours.
Thank you so much for having me and for the really nice intro, and go Bears. Hi, I'm Daniel Fried, and I'm excited to talk to you about inducing abstractions for agentic tasks. So agents are able to carry out fairly complex tasks in the world, but they shouldn't have to start from scratch on each new task every time. There's a lot of structure that's shared across tasks, and we'll show how agents can learn this structure online and use it to carry out tasks more successfully and efficiently. So LLM-based agents are able to carry out actions in the world, for example, to retrieve information or make changes on your behalf. And we'll see some more complex examples a little bit later, but as a simple example, maybe you go to ChatGPT and ask, what's the weather this week? And it'll go off in the background and take some action on the web and get the weather report and return that to you in a structured format that it can then, condition on as it continues the conversation. But there's a lot of questions here about what are these actions that the agent is taking? What's the right space for them to act in? And what's the right level of abstraction for the actions to be at? So one possibility is to give the agent access to the same interfaces and actions that people use on the web, a graphical user interface. And we've seen a lot of work on this recently, a lot of commercial products like OpenAI's Operator, Claude's computer use agent, Manus, and a lot of others too. But you can think about these as the agents using essentially keyboard and mouse actions. It would go to google.com, click in the search box, type weather today, type enter, get back some information, and send that to the user. And there's a lot of advantages of this. I think the chief one is that these agents can use interfaces that were already built for people. And these interfaces, let people carry out a really wide range of tasks on the web. It's their main interface to the digital world. But there's a lot of downsides too. So one of these is, the tasks are very long because you're taking these very low level actions. So there's a lot of chances for the model to go wrong. And since the trajectories are long, as models get more capable, it might also be harder to verify and reason about what the model's doing. Another big limitation is there's no explicit reuse across tasks. So the model's starting fresh on every new task. And for example, if you're searching for the weather tomorrow or the weather in a different city, there won't be explicit reuse of what you've done successfully in the past. So we can contrast this with higher level actions that might be provided by tools or APIs. So in the case of the weather, there's sites like weather.gov that have APIs available. So there's like a function, check weather, that's behind a web portal that the agent can issue a GET request to, and that function will return the information that the agent can then use. So these tools and APIs are really great. They help to shorten the task horizon. So there's fewer actions for the agents to take, fewer chances for it to go wrong, and also make it potentially easier either for a person or an automated system to verify that the agent's doing the right thing. But a big disadvantage of tools and APIs is that they need to exist for a particular task that a person's trying to carry out with an agent. And this often isn't the case. But the main idea of this talk is that we can have the model carry out low-level actions. And this will be really general, let the agent carry out the same, at least in theory, carry out the same tasks that a person could on the web in an interface. When the agent predicts that it's gotten a task correct, we can abstract out a high level, what you might call a skill or a tool or a workflow from the sequence of low level actions. Basically, just an abstraction of part of the behavior that the agent can then reuse to improve its success and efficiency on future examples. And this is a pretty old idea, so it's spiritually similar to some ideas from reinforcement learning, like options or hierarchical policies, and also a lot of work in program induction. The details of our work are very different from those, but the idea is conceptually similar. And the idea has also gotten a lot of popularity recently as skills for LLM agents. Our work predates the use of skills a bit, and we also focus really heavily on how to represent skills, comparing textual workflows with programmatic representations. And we show that these skills are helpful for general purpose GUI agents. But before getting into the methods that we'll propose, let's look at some of the settings that we'll be working in. So benchmarks and sandboxes for realistic web tasks. And the settings will be two benchmarks that we built at CMU. The work was led by, they were then students, Shuyan Zhou, who's now a professor at Duke, Frank Xu, who's at Microsoft, and my PhD student, JY Ko. And as an example of the sort of tasks that we'll be having agents carry out in these environments, here's a demo that we made a couple years ago of a task: navigate to the page of a good Thai restaurant in Pittsburgh that meets these criteria, pick the one with the highest rating. And the agent will carry this out by taking actions in the browser. So it goes to yelp.com, it'll click in the search box, type Thai restaurant, search for it, and once it gets the list back, it'll scroll through the page and find one that meets these criteria and then go to it. And then it'll stop and return to the user. And so in this case, it's a success. We wanted to evaluate how good agents were on tasks like this on as realistic websites as we could get. So we built a couple benchmarks for this called Web Arena and Visual Web Arena. And these benchmarks are based on real world sites. So we took open source implementations of complex websites for classifieds, a Reddit clone, a shopping site, GitLab as well. And we sandboxed them in Docker containers so that agents could safely and reproducibly make changes to the environments as they're acting in them. And then we wrote tasks for the agents to carry out in these environments with natural language descriptions, like the ones you see here. And we also wrote evaluators to see if the agents carried out each task correctly. And we hand constructed all of this. When the agent's acting in these environments, it has a couple different representations of the observations. So one is, what people see, the pixel-based rendering of the web page. It also has access to the HTML and what's called an accessibility tree, which is a simplified version of the HTML. And the action space that it's using to act is really low level and very similar to what people would use when they're interacting with these pages. It has click actions, hover, as well as things that you would do with the keyboard and tab and history control. And I'll show some examples of the tasks that we're having agents carry out in these settings. Some of them are more information seeking, like this one, finding information about this particular company. Others are much more open-ended, like add something like what the man is wearing to my wish list, along with this picture as input as part of the task. And the key thing when using a simulator that an agent can take actions in is that the evaluation needs to account for the tasks being very open-ended. There's a lot of different ways that you could achieve a single goal. So for something like this task of add what the man is wearing to my wish list, Our evaluation function that we use to check if the agent got it correct actually needs to look at what's currently in the agent's wish list, pull out the image from it, and then feed it into an off-the-shelf visual question answering model that we use to ask, is this a polo shirt and is this shirt green? So that, there's multiple possible green polo shirts that the agent could find in return, which would all be good solutions. And this will help us to account for that open-endedness. So that's kind of a high-level overview of the setting. The agents that are acting in here, the base agents, are using multimodal LLMs. And this is pretty similar to, computer use agents and other models that are currently deployed. We were building this in 2024, and so the representations that we were using, take in the user goal, text as well as an image in some cases, and also condition on the observation of the web page that the agent is currently on for this given time step. Well, at the time when we did this work, it was helpful to represent these web pages using a set of marks representation. So we'll annotate the web page with basically the bounding boxes and identifiers for those, the things that the agent can click on and interact with, and also annotate those in the accessibility tree for the page. We'll feed all of this into a multimodal LLM, which will then predict a chain of thought, and finally produce an action in this very low-level action space that will then be taken by the agent, which will move it to a next page, and this process repeats again. So that's the general setup for Web Arena, Visual Web Arena, baseline agents for it. And here's how the progress on this benchmark Web Arena has progressed over the past couple of years. So we see that success rates started off pretty low, but really ramped up quickly. And human success rate on these tasks is around 85%. But we can look at like multiple phases of progress here. So one is just improvements to kind of the raw LLM or multimodal LLM that's being used as the backbone for the agent. Other improvements you can broadly characterize as improvements to the interface that the agent has. Improved action spaces that maybe compress things a bit and are more accessible to the agent. And there's also been a lot of improvements, particularly recently due to improved agent frameworks. Two of the ones that I'll be talking about in this talk are agent workflow memory and agent skill induction. And both of these methods were ones that we developed that rely on learning and reusing the structure of tasks as you are solving successive instances in the benchmark. So the motivation for these approaches is that part of the reason that web tasks are hard is that they can be really long horizon. So you might have a task like create a repository with this name that has a README file that links to this information that I got on another website. And to carry this out, each part requires a lot of steps interacting with a particular site, like creating the repository takes multiple steps on GitLab. You have to then create a file within it and retrieve information that you'll put into the file. So to do well on these long horizon tasks, it's potentially useful to learn how to compose the atomic actions that make up some of these subtasks, like creating a repository, creating a file, and retrieving information. And the method that we'll use to compose these atomic actions together into abstractions is to learn skills. So you can think about this with a motivating example of like finding a place by its name using a maps tool on the web. And to do this, you'll need to go into a search box, type the name of the location that you have in mind, and then click search for it. And this is sort of a representation of a particular subtask that could be reused in other contexts as well. So if you want to get the zip code of a place, the first step there is to find the place by its name, repeat these same actions again, but then augment it with some additional steps, like searching to get the zip code from this extracted information and then sending this back to the user. And the key ingredients in any approach that learns to use these sorts of subtask abstractions are first how to represent the abstractions, how to induce them, how to store them, and then how to use them to improve the agent performance in the future. In this talk, we'll be focusing mostly on how to represent these subtasks. And the other parts of the approach, like how to induce them, how to store them, how to use, will show that pretty simple techniques that use LLMs are actually able to go really far. And the main thing that we'll be doing is comparing textual representations of these subtasks with programmatic representations, basically using functions to represent the subtask abstractions. The setting that we'll be operating in is basically an online learning setting. So a lot of the past work on agent benchmarks typically treats the benchmarks, the items in the benchmarks, as being independent from each other and identically distributed. But this leaves a lot on the table because when we're actually using agents, we want them to adapt to the tasks that we do, the websites that we use them on, and sort of continually learn to carry out tasks better and better. So we'll be operating in an online learning setting where we'll have a memory that's going to be maintained by the agent across the tasks that it tries to carry out. And we'll pass these task examples in a stream. And the agent will try to solve the task. And if it seems that it solved it correctly, it'll induce an abstraction, a skill from that example, store it in a memory, which will be increasingly growing over time. And it'll use that memory to improve performance on the future examples that it comes across. And we'll operationalize this in two different approaches. Both of these were led by my PhD student, Zora Wong. And the first paper, Agent Workflow Memory, focuses on using textual representations of these subtask abstractions. And the second one shows that we can also use programs as an effective representation, which has some benefits that we'll talk about in a little bit. So we'll start off by learning workflows online, textual representations of these repeated subtasks that an agent might carry out. So as we saw a couple slides ago, the agent's going to be maintaining a collection of workflows, representations of these subtasks that'll be growing over time as it sees new examples. And if the agent carries out an example and predicts that it solved it correctly, it'll induce out a reusable representation of part of that task that might be useful in the future. It'll store it in a memory and use this memory on future examples. So the way that we implement this uses just it's pretty simple and it uses just a lot of the standard machinery of LLMs and agents. We'll have the agent have the query, the description of the task that it needs to carry out, and it'll predict these low-level actions by acting in the world using this loop that we saw earlier. Taking an action like clicking on this particular element, that'll update the state. It'll take another action, clicking on a different one, until it's produced a complete trajectory in the environment. So this is a possible completion of the task. And we'll want to pull out a representation of some part of that task, but only if we believe that the agent has solved the task correctly, which would give a signal that all parts of the task are probably correct and could potentially be reused. So we'll use an LLM-based judge that takes in the final state that's reached by the agent and also the natural language query and predicts, does it seem like the agent has solved the query correctly? If not, we'll just move on to the next example. We won't try to induce any workflows from this example. But if we predict that we did get it correct, then we'll feed in the trajectory to an LLM. And this LLM will have few-shot examples of workflows of potentially reusable sequences of steps that are part of trajectories. And the LLM will try to pull out workflows that correspond to this particular trajectory. So the workflows look something like this. They have a description of the subtask. They also have sort of chains of thought that describe the purpose of the actions in the parts of the trajectory, and then the actions themselves. So the LLM induction module will predict this workflow or multiple workflows, and we'll take those and we'll store them in a memory, which is just a text-based collection of these workflows that's going to be growing over time as we see these examples. And we'll also, when the agent's carrying out tasks, we'll have a condition on the memory too. So this is just another reference that the agent can refer to as it's producing these low-level actions. It can potentially copy and potentially modify some of the actions from appropriate workflows that it sees in the context. So this approach is pretty simple to implement, but we find that it's pretty effective too. So here's an example, or here's an evaluation on a set of tasks from WebArena that all involve using a map tool to carry out various tasks. And so the x-axis here presents examples from that use this map tool in a fixed ordering. And we're going to be showing the cumulative success rate on the y-axis here. So a baseline agent, which doesn't have a memory and doesn't have these workflow representations, is in blue here. And I'm going to show tasks that are correctly solved by the agent as it solves them. So this baseline agent's able to find a place by its name, find a cafe near a place. But when we compare it to our workflow memory-based agent, which when it predicts that it solved a task correctly, stores a representation of parts of the task, that workflow memory agent's able to substantially outperform the baseline agent and fairly quickly too. So it's able to carry out more complex tasks like getting the coordinates of a place, getting the zip code of a place, and moving on to things that are quite a bit more complex, like finding a hotel near this location and finding shortest walking paths, which aren't able to be solved by the baseline agent. So the key here is these workflows are reusable and they're also somewhat abstract. And here are some examples of workflows that are induced by our method. So for example, finding flights, the workflow here might be entering flight locations into the particular search tool. And we have some experiments in the paper that show that these workflows can also generalize across different websites and even across different domains as well. Although it works best to apply workflows in the same site that they're induced in. Um, and really, this is kind of like improved by the agent's ability to adapt online as it's interacting with a particular news site that it has access to. So evaluated on the WebArena benchmark, we find that our method, workflow memory, substantially outperforms approaches that don't have this memory and subtask representations. And actually compares does slightly better than this really nice method called STEP. And STEP uses also representations of useful subtasks, but these were written by people in a way that's kind of like appropriate to the website. So you can think of them as being sort of like a human constructed API. And we find that our approach, which induces these representations without using supervision from people, just using the induction module and the LLM-based judge that predicts whether you got a trajectory correct, is able to outperform this a bit. Okay. So we've seen that agents can induce and reuse workflows to improve performance on future tasks. But there's some limitations to workflows too, which we'll address in this next somewhat short part of the talk by using programs, using functions to represent these subtask abstractions. And this is also work that was led by Zora. So textual workflows look something like this. They have a description of the task that you're trying to carry out, and they also have the sequence of actions that were used to carry out that subtask in a particular context. These sort of textual workflows are nice because they're flexible. So the agent is going to have this workflow in the context window and be able to refer to it as it's predicting actions for some new states and some new tasks. But it'll refer to that workflow and it'll still need to predict actions one by one. Some of those actions could be copied from the workflow with some modifications, but it's not going to do too much to improve the efficiency of the agent. And we're also not going to be able to really reason about whether a particular workflow was called or not, because sort of everything is just in the context window and potentially copied from. As an alternative to this, we'll try out programmatic skills. So a way that, and this is a real skill that's induced by the method that we'll talk about in a minute, but a programmatic skill for searching for a product would be a Python function, which takes in some arguments like the search box ID in the particular web page that the agent's in and the query that the agent should search for. There will be a doc string too to make it easier for the model to know when to use the function and how to use it. This doc string is going to be model generated. And then this function will call the low-level actions that are available to the agent, but also potentially call other skills that have been induced in the past. So things can be hierarchical here, which is another nice advantage of programs. And when we have these programmatic skills, we can actually just call them in the same way that agents call tools. So the agent could generate a call to the search product function along with some arguments. The agent could then hand off control to the environment executing this skill and any other skills that it calls and the low-level actions, and then returning control to the agent. So this is going to make things a little bit more rigid, right? Like we can't deviate from the behaviors that are produced by calling this function. The agent just calls it, hands off control, and then control comes back to the agent. But if the programmatic skill is a good fit for what the agent needs to do next, then it's great because we don't have to predict the actions one by one. And we can leverage all the tool calling machinery that agents have and are already trained to be good at. So how do we get and use these programmatic skills? Well, the method's actually really similar to the method that we used for the textual workflows in the last part of the talk. So the agent is going to have this natural language task description to carry out. It'll produce the action trajectory by taking actions one at a time in the environment. And then we're going to take that trajectory and prompt a strong LLM that has good code generation abilities with a few shot prompt that asks the LLM to produce potentially reusable functions that abstract some of the behavior of this trajectory. So for example, this trajectory might cause the induction LLM to produce a search reviews function, which looks something like what we just saw, and an open marketing reviews function, which would be particular to this specific website, but would be usable in the future. So along with producing these programmatic skills, this induction model is also going to produce code that calls those skills to produce the trajectory, to try to replicate the trajectory that we are inducing the skills from. And this code will call these skills that have been induced, but can also call other skills that have been induced in the past, as well as the low-level actions that are available to the agent. So we, just as before, we want to induce skills from trajectories that we think are correct. And so here we'll execute this test code, which calls the skills. That'll get us to a final state in the environment. And then, as before, we'll use a model-based judge to predict, does this state seem to be the correct one for this natural language instruction? And if so, we'll take these induced skill functions and we'll store them in the memory, which is just here, you can think of it as an increasingly growing toolbox of things that are useful for the agent to carry out these subtasks. So there's some results in the paper showing that this programmatic approach helps on Web Arena, and it does better than the textual workflows that we looked at in the last part. But I think one setting, as you might expect, where it's potentially helpful is on tasks that have a little bit more programmatic structure to them. So we looked at a set of tasks which are still naturalistic, but involve things like changing multiple addresses. Here's an example. Can you change my billing address and also update my shipping address? And a baseline model here has to carry out actions one at a time. And this produces a very long sequence of actions. The agent may even run out of the context window in order to carry out this task successfully. Textual workflows do help by giving the agent a template to refer to for updating the address. But if we use these programmatic functions to represent the subtasks, if the agent has a navigate to address settings function that it's induced on a previous example, it can just call that and carry out that part of the trajectory in one step. Then call this update address details tool that's been induced twice and solve the task much more efficiently. So on the set of what we call scaled up web activities that are still in the Web Arena environment, we find that in comparison to a baseline, using textual workflows substantially improves success, but using these programmatic skills helps even more. And both approaches improve the efficiency of the model, so the agent needs to make fewer predictions in the environment. Workflows are helpful for reducing steps just because the agent doesn't go wrong as much. So it solves a task correctly, which results in a shorter trajectory. But skills substantially improve the efficiency because the agent's able to hand off control to these functions to carry out the task. And so some of the takeaways from this part about using these programmatic representations of these subtasks are that LLMs are really good at code generation, and also so like writing functions that abstract behavior. And they're also really good via tool calling at using these functions. So we can leverage these strengths of LLMs to induce programmatic skills. And we find that these programmatic skills are a good fit for web tasks. And these skills can be called as black box tools, which helps to improve the success and efficiency of the models. But I think there's a lot of future work to do here. We can think of this as kind of a proof of concept, but we're inducing these functions based on using a model-based judge of whether the state produced by calling the function seems to be correct. There's a lot of tools from other communities that could be used to analyze whether, how functions relate to each other, pre and post conditions on functions, and do more sophisticated verifications of what the agents are inducing. There's also a lot of room to take into account that functions should be reusable. We're right now just kind of like adding these functions into an increasingly growing library, but it would be really well motivated to refactor that to try to compress the trajectories that the agent needs to carry out and do this more efficiently in the future. And now, in the last part of the talk, I want to kind of shift a little bit and look at comparisons between how people and agents carry out tasks. And we can use the abstraction learning machinery that we've talked about earlier on to look for high-level correspondences between the way that humans carry out a task and the way that agents carry out a task. even if the humans and agents differ a lot in the low-level details of how they carry out individual steps and subtasks. And this is again work that was led by Zora, and also in collaboration with Graham here at CMU. We co-advise Zora and Dee Yang, who's at Stanford. So we're interested in, agents are getting better on tasks and operating in real world settings. And we're interested in like how close are agents to be able to carry out some of the real world work tasks that people need to do. So to study this, we'll source some tasks that are used in really common US jobs. So there's this database called ONET, which is maintained by the government and has a collection a lot of the tasks that humans need to carry out in a variety of jobs, along with estimates of how common these jobs are. And we'll take around 15 tasks that are inspired by these categories and that we tried to design to be realistic. We'll sandbox the tasks in a similar way to how we sandboxed the tasks in Web Arena. And these tasks will cover basically 5 different main domains. So data analysis, software engineering, administrative tasks, writing, and design. We'll take each task and we'll assign them to professionals who we recruited from Upwork, whose normal jobs are in these areas. And we'll also take each task and assign it to an LLM-based state-of-the-art agent. So we'll have 3 professionals on each task. And we'll also use these general purpose agents, the ChatGPT agent, Manus, as well as OpenHands, GPT-4o, and Claude Sonnet, which at the time that we did this work were state of the art. So agents and people are going to be carrying out the same tasks and have access to the same environments to do it. And people are going to generally be using these keyboard and mouse actions, which are very low level. So it might look something like this, kind of just the raw stream of events that you get from a person trying to carry out a task. And these tasks are somewhat long horizon. I think the average task length was around an hour. So to be able to analyze this and look for correspondences between the ways that people are doing the tasks and the ways that agents are doing the task, we'll use the workflow induction machinery that we had from the first part of the talk. So we'll take this raw action trajectory that was carried out, and we'll prompt an LLM to produce these workflows. So if we do this one time, we'll get workflows that look something like this. Create a new Google Doc file. You're able to use the state that was that the agent carried or the person carried out these particular actions at in order to know that it's creating a Google Doc in particular, and then updating the title. Since these tasks are really long horizon, we'll actually do this hierarchically. So once we've induced this first level, we'll prompt the workflow induction module again to output these higher level workflows, like writing a report about AI agents, and then for some later actions, creating slides to present it. To all complete this overall task of writing a report about AI agents. So we'll do this both for the human trajectories and the agent trajectories, trying to carry out the same high-level task. And we'll look for alignment between the workflows that people use, the sequence of workflows that people use, and the sequence of workflows that agents use. As we'll see a little bit later on, the way that people and agents carry out individual workflows can be very different from each other. But at the high level, at the sequence of workflow level, there's actually a pretty general correspondence between the human way and the agent way of doing the tasks. So for example, this task starts off generally by reviewing some data and then developing visualizations, creating some analysis of them, and then presenting the information. We did an analysis of how well these sequences of workflows match with each other by looking for pairwise alignments between the steps and the workflows. And we find that although it differs from the domain that you're in, with design being the lowest and software engineering being the highest, um, and although it also differs between whether you're looking at human versus human, human versus agent, agent versus agent, there generally was a high degree of correspondence in the sequence of workflows that are being carried out. But I think some of the really interesting differences are in the way that the individual workflows are carried out. And we found that agents, these state-of-the-art agents that have access to, the full GUI that people do, agents like ChatGPT's agent, which is similar to Operator, Monis, even though the agents have access to these GUI applications, they will pull up a terminal and start carrying out these tasks programmatically. And in a lot of cases, this makes sense. So, like for data analysis, the human might carry this out in a Google spreadsheet, but the agent is going to pull up pandas and do this in a notebook or in a terminal. And for data analysis, that makes a lot of sense. For slide presentation, the person might use Google Slides. The agent, and across a couple different state-of-the-art agents, they actually prefer to use the Python PPTX library to design the slides, which, is starting to push it a little bit. Uh, for logo design, there's a preference for agents to use matplotlib, and it's actually very challenging to make compelling logos in matplotlib. And for interior design, agents will prefer to use an image generation model. So we find that agents, I mean, maybe it makes sense because these backbone LLMs were trained on quite a bit of code, but the agents are preferring to use programmatic approaches rather than using the same interfaces that people do. There were also some interesting qualitative findings that we had. These aren't super related to workflows, but I think they're just kind of fun and motivate future research. So agents we found on these long horizon tasks do pretty fancy things to cover up their own shortcomings. So we have a task like the company's gone on several team lunches and dinners, help record and organize these receipts. And the agent confirms that it can do this and describes the plan. The agent's actually not very good at OCR, and so it tries to process these images of the receipts, and the receipts correspond to these restaurants, these 5 restaurants. But the agent is not able to extract that information from the receipts and hallucinates a different set of restaurants and data for them. Now, it's kind of interesting because I wouldn't call this lying. The agent actually says, I'm going to create realistic receipt data for team outings, but maybe this is kind of a interesting form of reward hacking. As another example, you could ask the agent to navigate to this folder that has these 10,000 reports and create 10,000 reports, create a summary report from them. The agent again struggles with information extraction here. So it actually decides to do deep research on these companies that we already have the reports for. It tries to find the reports for them just on the web. So maybe from these results, it's not too surprising that humans still are more successful on these realistic work tasks that we sourced, even compared to these state-of-the-art agents in the overall success rate on the tasks. But we do find that agents are able to carry out the tasks quickly. So they're around 90% faster than people at carrying out the tasks. And when you compare wages to API costs, agents are, as you might expect, cheaper as well. But they're fast, they're cheap, and they're also sort of out of control currently, as these results showed. But I think the findings that we had that showed that at the high level, the sequences of workflows generally align between humans and agents suggest interesting future work that we could do on improving human agent teaming. So here are visualizations of how the amount of time that was spent in each workflow for these aligned workflows between humans and agents. And there's some tasks that people are much faster and more successful at in comparison to agents and vice versa. So we could potentially improve accuracy and efficiency by switching between humans and agents at the subtask level, which I think raises interesting questions of, how to identify who should do what based on skills and expertise and preferences for the people, as well as like how to hand off these subtasks from one to the other, which raises really interesting questions of like managing context and knowledge, and how do you like have a person sort of like drop in order to fix what an agent is doing without having done that part of the task themselves. But the overall takeaways that I want to leave you with from this set of papers is that tasks, real world tasks, have a shared substructure, and we show that we can leverage this substructure. We can induce it automatically, represent it using one of a couple different methods, either textual workflows or programmatic functions. Um, and these abstractions of tasks help to improve success and efficiency of agents in these long horizon realistic settings. But I think that, the web arena tasks that we've looked at, and even the more real world work tasks that are around an hour long that we analyzed, are still pretty limited. And we really want to move toward agents that can learn over extremely long time horizons, like years of interaction with a person in a variety of settings. And those settings will be changing, as the person moves through different things in life and in work. Um, so skills and these abstractions can help to adapt agents to new environments and new tasks, and store and reuse information. But for these really long time horizons, we're going to need something more than just non-parametric memory, just storing things in a memory that grows over time. And I think there's a lot of work here that we can do on modeling to try to make this tractable. But I also think that these abstractions give a really nice lever for improving interactions with people. So these abstractions are reused by agents across future tasks. And so they give people a way to do targeted corrections of entire classes of model behavior. And we see examples of this now where people are like writing skills for Claude Code and putting those skills into shared repositories, sharing them with other people. But we're going to need better as these skills are induced by agents for very complex tasks. And as the skills become very complex, we're also going to need better methods and multimodal interfaces for letting people review and correct these skills. Not just the skills themselves, but also kind of the skill in all of the different contexts of use that it can have. So I think that there's really interesting, algorithmic and HCI problems here that the community needs to tackle. So this was work with a lot of collaborators. These are kind of the main students who led the work and the PIs, Zora, Shion, Frank, JY, Russ, Graham, and DE. And thanks to all of them, and thanks to all of you for listening. You can find links to Zora's code bases for the induction approaches at these links here.
All right, cool. Thanks, Daniel, for this insightful talk. That comparison between human-centric UI approaches and the agents' programmatic approaches offers really fascinating lens of how we think about model training and AI teaming. So as folks are preparing for the questions, and if you do, please feel free to use the raise a hand button. Let me kick us off with a question myself. So from the continual learning perspective, and you also mentioned that agents could be in the future be training for extended long period of time. How do you manage the life cycles of these skills? And specifically, do you see any negative transfers of the skills or skills that become obsolete that could deteriorate the performance? So I'm curious about, if you have any mechanisms in mind of updating or pruning these skills.
Yeah, that's a great question. So we have not yet investigated that in these web settings. I could totally imagine that as you get a really large number of skills or tools, it could degrade performance as the model is no longer able to choose the best tool to use. In some prior work that Zora did, it was called Trove, that used somewhat similar function induction approaches for question answering. We did prune the set of functions that was induced. And we just used kind of like a frequency-based approach for that, like a least recently used cache type approach. So that if a function hadn't been used in a long time by the system, it would be removed. But I think that also leaves a lot on the table. We should be refactoring the learned abstractions so that as we have functions that share um, functionality, we could rewrite those as a single function. So, approaches that kind of like operate continuously on the abstractions and try to compress them while still maintaining their correctness and their ability to carry out and replay some of the trajectories that you've seen in the past. So yeah, I think there's a lot of work that could be done here. I think we need some more benchmarks also for evaluating models' ability to refactor code that's been generated. And there's some really nice work on a benchmark for this. I forget the first author's name, but Justin Chu was one of the authors on it, where they develop a benchmark for modeling or evaluating LLM's ability to like take code and refactor it to minimize it. So yeah, I think we could do a lot of work on that in the future.
Okay, cool. Yeah, that seems to be an open problem the field could tackle. So yeah, so I see we have Jai here. So Jai, you raise your hand. Please feel free to go ahead ask your question.
Yeah, thank you for the presentation, Daniel. Actually, my question is like you are abstracting the skills from a particular task, let's say like searching on the web or like finding the pin code. So, like,
Mhm.
like what did you notice? Like these tasks, like these abstraction are generalizable to other tasks, like the similar task, or how generalizable are those abstractions that you like made from particular tasks?
Yeah, that's a great question. So I don't have a slide on this, unfortunately, in this talk, but in the agent workflow memory paper, we did do an analysis of how well the skills transfer across sites. So to do this, we use this benchmark called Mind to Web, which has trajectories that were produced by people across a really wide range of sites. This is really nice work from UC's group at OSU. Um, and we partitioned those trajectories into ones that were in the same domain, like shopping sites, ones that were in the same site, like Amazon versus some other shopping site, and then the lowest level was different tasks within the sites. And we looked at how much the workflows that we induced transferred across settings. So we like induced the workflows in, for example, one domain, and then we held the workflows fixed, but used them in another. And we did find some transfer. So performance was higher if we had those workflows induced on the different domains than if we didn't. The closer the transfer setting was, the more benefit you got, as you might expect. So it worked the best in order to if you were inducing the workflows on the same domains and sites that you were trying to use them. But we did get some transfer in all settings. So there is some stuff that's reusable, like searching or generic kind of navigation operations. But the thing that worked the best was to let the agents continue to induce new workflows in the final setting that they were operating in.
Also, like, is it dependent on the GUI? Like you have one website, particular GUI, and the other website have a different GUI, but both are shopping websites.
Yeah.
Uh,
Yeah, I think it definitely is. And we like our approach right now kind of only weakly encourages the model to induce the abstraction that's most useful for transferring broadly. I think like you could consider uh, maybe inducing multiple versions. One which is kind of like tailored to this particular site, so it'll be more efficient for the agent to use. And another which would be more generalizable that kind of like doesn't hard code as much about the site, but could still be useful for other similar sites that you could generalize to.
Yeah, thank you.
Yeah, good questions.
Okay, great. So I see Anu, you have your hands up. So go ahead, please.
Hi, Danielle. Can you hear me?
Yeah.
Awesome. Thanks for the great talk. I was wondering how do you sort of protect against duplicates, workflows, and skills being induced?
Yeah, good question. So when the agent is inducing the workflows and skills, I believe it has access to the existing workflows and skills. So it's encouraged not to induce one that's going to duplicate exactly something that's already existing. Um, then in not in these papers, but in this earlier work, Trove, that we did more explicitly uh, so what we did there was we have this toolbox available and we prompt the model in three different ways. So we say, generate a solution that does not use any tools at all. That's the first way. Second way is generate a solution which does not induce a new tool, but only uses an existing tool. And the third way is generate a solution that induces a new tool and uses it. So we force the model to try all three of those approaches, and then we compare the predicted accuracy of the solution as well as the length when we choose which one to use. So that will be inducing a tool if it's helpful to produce, an overall shorter solution. But if there's an existing tool that's a good fit, then that's going to be preferred by correctness. So we didn't do that in the agentive setting because we just wanted to do, single shot execution of the tasks. But I think exploring approaches like that could potentially be more helpful than what we're currently doing just with the prompts.
And to sort of get these actions itself, do you sort of give the full action space to the LLM to generate these actions, or do you depend on its world knowledge to generate all these web actions?
Yeah, good question. So the agent does always have access to the full action space in this work. So like that's the low level actions, like what you see here. And when we're inducing the programmatic functions like this, the agent would also have access to a list of all of the basically function signatures and doc strings of the functions that it's induced in the past. That worked for the settings that we're looking at here, but as that collection of functions grows too large to put that all in the context window of the LLM, you would have to do something more like a RAG type approach, where maybe you retrieve from the set of available tools based on a description of the state that you're currently in. Or other approaches could work too, but like RAG might be a good place to start.
Thanks so much.
Yeah, thanks for the question.
Hello, Daniel. So thanks for your great talk. I have a question for you. So I'm curious about how do we manage different skills? Maybe there are some skills have conflict, so maybe different objectives. So could we manage that to improve the performance?
Like merge skills that might have some kind of like similar structure, but different contexts that they're called it.
Right. Something like that.
Yeah, I think that's a great question too. So like I mean when we're programming and when we're refactoring code, we do something similar, like you would look for commonalities in functions and then extract those out into something that, maybe adds an argument to parameterize the things that differ between those two. I think we could also explore doing something like that here as well if we wanted to continue to do everything in the program space. But I think, the fact that we're not that we one approach, one alternative is to just call the tools, but another approach is to like let the LLM kind of refer to the skill and then modify it, make changes to it, and call it again, or like kind of refer to it and produce the low-level actions. So you have a lot more flexibility because these are LLMs that are ultimately mediating between the memory and the actions that are taken. So I think we don't have to just stick to kind of the programmatic approaches, the things inspired by refactoring or software engineering.
Yes, yes, thanks.
All right, great. I think that's it for today. So please, everyone, join me in giving Daniel another round of virtual applause. Thanks, Daniel, for sharing your great research, and thank you, everyone, for participation. Have a great weekend, and see you all next week.
Thanks so much for having me. Thanks, everyone, for the great questions.
Thanks, Daniel. Take care.
You too. Bye.
Bye.